Hello everyone, welcome back. In this lesson, we will discuss the concept of fixed ratio in exponential functions. Exponential functions are incredibly powerful and useful, and understanding the idea of a fixed ratio can help us generalize relationships between numbers and make predictions about future values. In this lesson, we will explore why there is a common ratio in exponential functions, how to use it to find the base of a model, and we'll even take a look at a real-life application to see this concept in action. Let's take a look. Before we start discussing the idea of fixed ratios, we're going to quickly review the idea of a common ratio when dealing with exponential functions. I have another video in the channel that goes quite in depth discussing the common ratio, and I will make sure to link that video in the description box below so that you can easily find it in case you want to go back and listen to that discussion. All right, so notice here how I am starting with the exponential function b to the x. At this particular moment, it is irrelevant to give b a value, just the base. We're going to keep it general as b. And the exponent, remember, carries the independent variable, in this case, x. I have started constructing a table of values where I selected a few of the x values that we're going to work with. And at the moment, I left the y column blank, but we're going to go ahead and fill that out. Notice that here I have the same table, and the y values are already included in the column. How did I get that? Well, keep in mind, here it is. Here is the expression for the function, b to the x. And wherever I see x over here, in this case in the exponent, that's where I will be substituting the x values that I selected. For example, if x is 0, I'm going to go ahead to my expression right here, and I'm going to substitute 0 in x. So I'm going to have b to the 0, and we know that b to the 0 is 1. When x is 1, I go back to the expression here, and I replace x with 1. So b to the 1 is just b. When x is 2, I'm going to have b squared. When x is 3, b to the third. When x is 4, b to the fourth, and so on. Now, what we're going to do, just as we did it before in the previous video I was talking about, we're going to go ahead and we are going to form ratios with consecutive y values. So for example, take a look at these two consecutive y values. I'm going to form the ratio b divided by b to the 0, which is really b, because b to the 0 is 1. b divided by 1 is b. Then I'm going to go ahead now and I'm going to form the ratio between these two consecutive y values. So these two right here. And that's going to give me b squared divided by b, which is equal to b. And then I consider the next two consecutive y values. That will be b to the third over b squared is equal to b. And now imagine that I continue creating those ratios throughout, then I'm going to end up getting the following final result. I'm going to get that the common ratio is consistently b. No matter which of the ratios I choose, as long as they are next to each other, I end up getting b, 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 b throughout. So the common ratio in this case is equal to the base. And it's very important to notice that I'm going one step at a time, from 0 to 1, one step, from 1 to 2, one step, 2 to 3, one step, and so on. The common ratio, that's why it's called common ratio, because the ratio remains the same. It doesn't change. So exponential functions behave in this way. They have a common ratio. And in this case, the common ratio is equal to b. So when we look at the same table that we just had before, now we can conclude the following. F of 3, for instance. So here, right here, when x is equal to 3, we conclude that f of 3 will be equal to b times f of 2. B, the common ratio, times the previous y value. So going one step backwards, f of 2. And what is f of 2? Well, f of 2 is b squared. And that gives us b to the third. So what this is saying is that if I know the common ratio, if the common ratio is equal to b, if I know that when dealing with exponential functions, I can always generate the y value at a specific value of x by using the common ratio in the previous y value, the y value that is one step backwards. Similarly, let's do the same thing with 5 right here. Notice right here, I can go ahead and say that f of 5 will be equal to the common ratio times the previous y value, in this case, f of 4. And that is going to give us b times b to the 4, which is b to the 5th. And I really want you to notice how this is indeed the case. B to the 5th is what we had as the y value, and b to the 3rd here is what we had right here as the corresponding y value. So pretty neat final result. So in general, I want us now to generalize this statement. In general, we can conclude that f of n is equal to the common ratio times f of n minus 1. And f of n minus 1 is the previous y value, going one step back. Again, just in case, remember that this is what we had before, right? We took a specific example, f of 3, and we noticed that f of 3 was equal to the common ratio times f of 2. So imagine that n is 3. So then what is n minus 1? N minus 1 is 2 in this particular case. But now we can actually generalize it as f of n for any particular n. We have that we can figure out f of n by taking the common ratio and multiplying it by f of n minus 1. Now, I want to make a further generalization here. In the previous cases, we were working with n. And n, in all of those examples in the table of values, if you think about the table of values again, I only chose natural numbers. 0, 1, 2, 3, 4, 5. But the relationship that we just developed works for any real number x, not just natural numbers. I don't have to stick to just natural numbers, 1, 2. I can have 2.1, 2.7, 2.341, and that relationship still holds. This is the relationship that I'm talking about. So now I can have, again, any real number. X can be any real number, not just natural numbers, not just integers. I can have any real number. And this over here is still true. It is still the case that f of x is going to be equal to the common ratio times the previous y value, 1 unit back. So, for example, what I'm trying to say is that if I have, imagine that x is 2.1. So if I have f of 2.1. And I know that common ratio ahead of time. Somebody tells me, here is the common ratio and this is an exponential function. So I know that common ratio and I know that my relation is an exponential function. Then I know that f of 2.1 will be equal to b times f of 2.1 minus 1. That's going to be 1.1. So the hope here is that you're going to know the common ratio and you're going to know the previous y value. And in that way, you can generate the new y value at 2.1. Now that we quickly reviewed the idea of a common ratio, let's talk about fixed ratios. I want you to notice that I have the same exponential function, b to the x. And I want you to notice right here that I have the same table that I just used in the previous discussion. Same x values, same y values. What we are going to do now is we're going to consider ratios, just like before. But instead of going one step every time, I'm going to go by steps of two, by two steps. So for example, let me start with b. I'm going to go from b, so from x equals 1 all the way to x equals 3. So I'm jumping by two steps as opposed to one step. And I'm going to form ratios. So I'm going to form the ratio with b and b to the third. That means x is 1, x is 3. So I'm going to have in this case b to the third divided by b. And notice how that is going to give me b squared. And now let me continue being consistent. I'm going to keep jumping by two steps. So I'm going to go from b to the third to b to the fifth. We are going to find that if we go from b to the third to b to the fifth, notice over here, I'm forming the same ratio. I get the same outcome as before. I get b squared. And this is no coincidence. Whenever you're dealing with exponential functions and you decide to consider ratios that are the same number of steps away from each other, the ratio remains fixed. But the difference is that now you end up having a power. It's not like the common ratio. The common ratio was just b. Here you end up getting a power with b, but the exponent tells you pretty much the number of steps that you are involving. So if I'm going by 2 steps, the exponent becomes 2. If I were to go by 3 steps, the exponent will become 3. So then that means that the ratio will be b to the third. If I'm going by 5 steps, then the ratio will become b to the fifth because of the 5 steps. With the common ratio, the steps were by 1. If you remember, I was just going one step. So then the common ratio always became b, which is the same thing as saying b to the 1. But we want to keep the common ratio kind of separate. The common ratio involves only moving by one step. The fixed ratio is whenever we're moving by larger steps. So in this case, I'm going by 2 steps. So then the fixed ratio ended up being b squared. And like I said, this is no coincidence. This is how exponential functions behave. So here I have again the same table. And just very quickly to explore the new relationship that we get, we're going to go ahead and figure out what is f of 3 and what is f of 5. As it stands right now, let's go here to the left. F of 3, if you notice, is b to the third. But I want to see how I can get f of 3 by using the previous value. But not the previous value, the previous values 2 steps back, if that makes any sense. 2 steps back. So this is how we're going to do that. F of 3 will be equal to the fixed ratio b squared times the y value of 2 steps back. So in this case, it will be f of 1. And if you notice, right here on the table, when x is 1, f of 1 is b. So we're going to have b squared times b, which is equal to b to the third. And then very nicely, this is what we know the y value should be for f of 3. For f of 5, going back to the table, when x is 5, f of 5 should be b to the fifth. But I want to be able to show you how we can get the same thing by working with the y value 2 steps back and the fixed ratio, of course. So in this case, f of 5 will be equal to the fixed ratio, b squared, times the y value at, if we have 5 and we subtract 2 because of the 2 steps back, we're going to end up getting 3. So then that's going to give us b squared times f of 3. And if you go to the table here, f of 3 is b to the third. So we're going to have b to the third, which gives us b to the fifth. And this is exactly what we needed to get. So now to put things into perspective, to generalize what we just discovered. So in general, we conclude that if we have a fixed ratio, b to the c, obviously when dealing with exponential functions, so this is clearly all assuming that the model is an exponential model. So if we know that there is a fixed ratio of b to the c, and remember, c is telling you that's how many steps you are skipping. If we know that this is the fixed ratio, then hopefully we can conclude that f of x at any x value, not just natural numbers, any x value, I can have a decimal here, that's going to be equal to the fixed ratio times the value of the function c steps backwards. And again, just to remind you, when we were doing that just a while ago, we experimented beautifully with f of 3. And we noticed, like in that example, we were going 2 steps at a time. We noticed that f of 3 was equal to the fixed ratio, in this case b squared, and squared because of the 2 steps, times f of 1. And if you notice, 1 is 2 steps before 3. So same thing over here, right? I want you to really see the relationship. We have x, in this case, x is 3, and then x minus c becomes 1. Why? Because x minus c, in our example, x is 3, and c was with the number of steps, and we had 2 steps. 3 minus 2 is equal to 1. But now we can beautifully generalize the statement like this whenever our function is an exponential function. I want you to see here how we can put all of that into perspective when solving an application. Now, in this particular case, we are not going to solve the entire application. I just want to show you now how we can get information about the base of an exponential model by using the relationships that we just discovered in our previous discussion. How can we use all of that now to find information about the base of an exponential model in a real life application? So let's read it together. A cup of water is heated to 100 degrees Celsius and then allowed to cool in a room with an air temperature of 20 degrees Celsius. The temperature T in degrees Celsius is measured every minute as a function of time m. So here, the variable that we're going to use for time will not be T. It is going to be m, and m to represent minutes. So please know that m here plays the role of x. I'm going to even write it down just so that you remember. So m here is like x. And t, right here, if you notice, t is like y. But x, in this case, m is the independent variable. It is found that the temperature of the water decreases exponentially at a rate of 25% every 5 minutes. So every 5 minutes, the temperature of the water decreases by 25%. This is actually very important here. Very important. The rate right here. And that happens every 5 minutes. The temperature of the water will decrease by 25% every 5 minutes. Every 5 minutes. This situation follows an exponential model. They want us to find the base of the model. So here is the full model, right? The completed model with all of the relevant variables, but we're not going to find all of them. The only one that we're going to find is the base. In this particular video, we're just going to find the base. We will ignore everything else. I just want to know precisely, like they said, find the base. That's it. From the description that we just that was given to us, we're going to go ahead and use some of that information to figure out what the base is in this particular case. So we know that at 0 minutes, the temperature of the water is 100 degrees Celsius. Then we know that 5 minutes later, the temperature will no longer be 100% because the temperature is decreasing by 25%. That means that 5 minutes later, if you remove 25% from 100, you're going to have 75 degrees Celsius for the temperature. Since I know that this situation behaves exponentially, then I know that this decrease of 25% will happen every 5 steps. Every 5 steps, 25% decrease. Another 5 steps, 25% decrease. So I can already trust the relationship, the idea of a fixed ratio. I already then know that from here to here, I'm involving 5 steps. So the base, whatever the base is, b to the 5th is going to be the fixed ratio. And b to the 5th will be the ratio formed by taking 75, dividing it by 100, which really means that b to the 5th will be 3 over 4. And then when we actually simplify, in order to eliminate the exponent, we're going to raise both sides to the 1/5. And that is going to give us now that b, the base, will be equal to 3/4 to the 1/5. And now this becomes the base of the exponential model. So this is one convenient way that we have in order to determine the base of a particular situation by knowing exactly the rate of decrease or the rate of increase. By knowing how many steps this is happening, we can use the idea of a fixed ratio to determine in a very easy way the value of the base of the model that we're dealing with. All right, folks, that concludes our discussion on the fixed ratio in exponential functions. I really hope you found this video helpful and informative, and that it has given you a better understanding of how to generalize relationships between numbers and use real-life applications to find the base of a model. As always, feel free to leave any questions or comments down below, and don't forget to like and subscribe for more videos like this one. Thanks for watching, and until next time, bye everyone.